Hello and welcome to Introduction to Human-Robot Interaction. I'm Professor Carlotta Berry, and I will be your instructor for this course. Today we will review the syllabus, the course calendar schedule, a brief overview of robotics, as well as human-robot interaction. First, we will start with the syllabus. Everything you need for this course is available on the Moodle course website, shown here. The main thing that we will be looking at today is the course syllabus and the course schedule. But note also that under the first week, you will find the week 1 lecture, which I'm recording now. These will also be on YouTube. The slides will be under week 1 lecture. Lab 1 will be here, as well as a folder of the week 1 readings. You will need to complete all of these before you take quiz 1, which is the first class meeting of week 2. So first, let's look at the syllabus. So this will be a survey course in the field of human-robot interaction. The goal of HRI is to allow robots to successfully interact with humans. There should be some type of computational model to enable the robot and the human to naturally and intuitively interact. It will cover a variety of topics, but will have a special emphasis on HRI design because that's what you will do for your final project. And you will complete weekly readings, quizzes, labs, and projects on how to design a human-robot interaction system. And because HRI is interdisciplinary, there may be readings on topics from robotics, artificial intelligence, psychology, human-computer interaction, human factors, interaction design, education drama, cognitive science, design ethics, and other relevant disciplines. This course will include a lecture and lab component in order to explore the concepts presented on the actual robot platform. A new robot this year is the Blossom HRI robot, and potentially in the future a humanoid robot as well. So here's all the information in order to find me. Office hours are typically by appointment, or you can just stop by. There is no single textbook, but lots of readings as well as lectures. Upon completion of this course, students should be able to explain and to discuss basic HRI theory, terms, and principles, apply HRI principles to design a robotic system, and use practical knowledge of HRI to complete a research project and present it to an interdisciplinary audience during the final week of the quarter. You will be graded based upon your participation, 10%, quizzes 30%, labs and memos 30%, and a final project 30% as well. Please review the rest of the syllabus, and if you have any questions about anything, including the course policies or school policies, please come and see me. Okay. Next, we're going to go back and review the schedule. So the course schedule is as follows. Since this is a flipped class, we only meet twice a week for 2 hours because the expectation is those additional hours that you would typically be in a 4-credit-hour class. You are working on your robot. You are doing the readings. It's the same reason there are no exams, because all of your time should be committed to the readings, the quizzes, and doing the labs. So notice week 1 readings. It says due here, but they're really due before you take quiz 1. Also, to watch week 1 lectures before you take quiz 1. Lab 1 will be on getting all of the necessary software installed and working on the robot, including ChatGPT, and then being able to move the robot's head by using the 4 motors, using keystrokes as well as a Python script. And that will be due by Friday of week 2, where you will submit the lab 1 memo to Gradescope and also do the demo. So every 2 weeks, there will be a lab demo due, and every week there will be a quiz due, and there's weekly readings every week and weekly lectures. And then that will be for the first 8 weeks, and then weeks 9 and 10, you will work on your final project, which will be to design a human-robot interaction system that you will then recruit people to interact with to evaluate your system, and then you will write up your final project based upon the results of those interactions. All right, we are now ready to return to the slides. So now let's go over our weekly announcements. Lab 1 will focus on installing all necessary software and getting motors to move the head of your Blossom robot with keystrokes and a Python script. We have exactly 5 Blossom robots, so each student will get their own robot. You can leave your robot in DL202 and work in here, or you can take it home, but the robot is very, very fragile. So if you do decide to take it home, please just don't chuck it in your backpack or anywhere like that, because it will probably fall apart. So it may be better to store it in a locker here on campus and just work here or somewhere in the hallway. So once again, quiz 1 will be due on the Monday evening of week 2 by 11:59 p.m. on Moodle. Lab 1 will be due Friday of week 2, and Lab 1 demonstration will also be due Friday of week 2. Your weekly literature review, the purpose is to learn something about the state of the art for robotics and human-robot interaction, and become familiar with research relevant to the week's topics, and to practice reading research papers. Because I understand that you're undergraduate students, I try not to make the papers too difficult to follow, but you may have to read it more than once or take notes in order to really get the gist of it. So one thing that you need to read for week 1 is how to read a research paper by Wong, and then the 3 papers by Goodrich, Niemöller, and Yanko. Remember, this is not a programming class, but since programming is a prerequisite for this course, there is an expectation that you do know how to do programming and to practice. The Blossom robot will be programmed in Python. And if you have any questions, your teaching assistant, Anthony, absolutely knows the most about the robot, should be able to help you. If he's not available, I can try as well. So once again, the week 1 lecture is to summarize features of human-robot interaction, the types of human-robot interaction, review designer guidelines for HRI, types of robot autonomy, features of multimodal HRI interfaces, key differences between HCI and HRI, and human factors concepts that relate to HRI research. So where this comes from is my area of research is actually human-robot interaction. It was human-robot interfaces. So these top 2 images are actually screenshots from my dissertation, where I designed a human-robot interface in order to improve human-robot interaction between a remote user and a mobile robot. So the robot was located somewhere in a building, and the user had this interface with a sensory egosphere, which represents the robot's center ego and everything that the robot could see. And the user had to drive the robot based upon the map and the sensor feedback, and also be able to use situational awareness and reduce their mental workload to figure out what the robot could see and do. So these videos are other examples.
Tonight on RoboBats, we got 5-time world champion.
And so here's another example of people using a human-robot interface, just a video game, in order to drive a robot. And I also show this video often because I want to make it very clear, once again, that your robot is fragile. So you have to be careful not to do this, because we only have those 5 robots.
Make it a Bud Light. Oh, no mercy!
And the second video is this one, and that one's not working right now, so we'll skip that one. So what is a robot? A robot, simply put, is a machine with some level of autonomy, from teleoperation, which means it can't do anything without human intervention, to fully autonomous, which means that it does not need human intervention or direction. Typically, robots are somewhere in between, and that's called semi-autonomous. And where a human typically will help is sometimes with perception. So a robot may be fully programmed to do some things very, very well, like a Roomba vacuum cleaner, unless, of course, a cat is riding on it and it now is stuck and cannot move, or it cannot adequately vacuum. So the human's perception may have to step in to shoo the cat off, etc. A robot has embodiment, and the reason this is important now is because there are things called web bots, which is a different type of bot. So embodiment means that a robot has the type of body that it needs for the task it's designed to do. For example, a quadcopter maybe a robot that needs to fly in order to for a realtor to be able to scope out a subdivision, or a pool cleaning robot may have a body such that it can go underwater and be able to clean the pool, etc. All robots typically have perception, which means they use sensors in order to get some kind of perception or understanding of the world around it. And they will have some kind of action, some actuation that they do on the world in order to achieve some goal or task. And so the robot's components are typically based upon what it has to do. It may have a wireless link. It may also be wired, and it have a brain or processor, a microcontroller, a microprocessor, a computer, whatever that may be. It may be programmed in several languages: Sketch, C, Python, ROS, etc. And it will have sensors designed to be appropriate for what the robot's task is: vision, sound, touch, gauge. Your Blossom robot has a camera in order to give it vision, for us to do gestures. It has a text to speech as well, so that once we get the ChatGPT working on it, if you have a conversation with it, it can respond, etc. It can have actuators such as motors, hydraulics, pneumatics, as well as effectors. Effectors being a gripper, flippers, wheels, or the thing that affects the environment, and then the body, of course. So robots in the real world, like I mentioned, you can see Roomba, you can see a Mars rover. In the center, that is a Robonaut. At the top, that's a lawnmower vacuum cleaner. You could also have a RoboPack, such as the one on the military officer at the bottom right. So what is robotics? Simply put, it's the study of the field of robots. And in our case, we are focusing on human-robot interaction, which may be social robotics, urban search and rescue robots, museum robots, and many other topics. That top left one is industrial robots. The Sony Aibo on the right would be entertainment robots. Bottom center would be humanoids, and the top middle would be mobile robotics. So what is artificial intelligence? Artificial intelligence is the scientific understanding of the mechanisms underlying thought and intelligent behavior and their embodiment in machines. So how intelligent a robot appears is strongly dependent on how much and how fast it can sense and apply information to task. AI is the mechanism for planning and reasoning. So it requires an internal model of the world based upon perception. Knowledge representation, how do you represent that knowledge? That could be a map, a database, or something else. Some understanding of natural language is a big part of AI. Learning, that could be in deep learning, neural networks, machine learning, etc. Planning and reasoning for problem solving. Inference, being able to infer from information that's presented to it. Searching through possible solutions, having some hierarchical system organization, and some type of sequential program execution. So the robot control spectrum, a journey over time, started with sequential deliberative artificial intelligence in 1960. So this was sense, then plan, then act. Then it was soon found in the 80s that the world is its own best model, because in 1960s it required a very accurate map of a model of the world. So behavior-based control was much quicker. It was also the advent of human-computer interaction, and it was much, much faster. And then behavior-based control morphed more into hybrid control, where hybrid control also organized a little bit of the benefits of deliberative control with some of reactive control, that fast response from the 80s. And then in 2001 was the creation of human-robot interaction. So the robot primitives represent these control architectures. Sense, plan, and act, and how they are organized. And so they are represented in terms of deliberative control, hybrid control, behavior-based control, where sense is sensor data that becomes a perception or sense information. That information, sensed or cognitive, then creates a plan or directives for the robot. And then those directives become the action or actuator commands for the robot to act upon the physical world. So here are the robot paradigms again. The 1960s was hierarchical or deliberative control, very slow, sense then plan then act. Then in the 80s was reactive control, which was sense then act with no real plan or world model. And then it was determined that you actually needed a little bit of the benefits of both of these in the 90s, which became hybrid, deliberative, reactive control with some kind of arbitrator in between. And this was the birth of behavior-based control. So what is human-robot interaction? It's a field of study to understand the design and evaluate robotic systems by use by or for or with humans. And that was defined by Goodrich in 2007. And remember, it was formally defined as a field in 2001. And the objective is to develop principles to allow for natural, effective communication between humans and robots. Everyone doing robotics has one way or another to show HRI. It's a highly speculative field with some abstract frameworks, which may be difficult to create. And it may be based upon the application and the study and perception of how you want to have action maps and the data exchange between the environment, the robot, and the human. And that may also dictate what sensing acts you need. So it is a highly multidisciplinary area because it draws from a wide range of fields such as artificial intelligence, informatics, psychology, sociology, robotics, linguistics, cognitive science, etc. Human factors and anthropology as well. Their technologies are no longer just a function as a tool, because it depends on the humans and what the humans need to do with them. Because it not only involves the creation of a robot, but algorithms, programming, testing, evaluating, refining, and maintaining the robot. And so it may also involve things like human factors, natural language, and where human-computer interaction and all of those things come together. So once again, because it is a multidisciplinary field, here's just a sample of some of those fields: mechanical engineering, electrical engineering, computer science, robotics, human-computer interaction, cognitive science, etc. So now let's talk about types of interaction. You could have remote interaction or proximate interaction. And notice down here, it could be used for remote would be like the Mars rover, which is looking for soil or water on Mars. Proximate interaction could be you're using it and you're somewhere close to it. So remote interaction means the robot and human may be separated spatially and or temporally. Proximate interaction means the human and robot are co-located. Remote interaction is referred to as teleoperation or supervisory control or telepresence. And remote interaction with a manipulator is telemanipulation. So social interaction includes social, emotive, and cognitive aspects of interaction. Like I talked about in my dissertation, mental workload and situational awareness become a big part of remote interaction because the user may become mentally exhausted and stop being able to do a good job. And situational awareness is, are they really aware of where the robot is and what's currently going on, since they have to do this through a screen or remotely to figure out what's going on. Normally in social interaction, the human and the robot are seen as peers or companions and trying to work together, which means that it's once again semi-autonomous control. So the 3 laws of robotics can be broken down into a designer guideline for HRI as well. And it is: a robot may not injure a human being or through interaction allow a human being to come to harm. A robot must obey the orders given to it by human beings except where such orders would conflict with the first law. A robot must protect its own existence as long as such protection does not conflict with the first or second law. These laws have been added to since Isaac Asimov first created them in I, Robot. And there's now a zeroth law that adds on humanity, but we won't discuss that here. So interaction attributes include the level of autonomy, the nature of information exchange, how the robot's level of autonomy, as well as how are you exchanging information. Is it gestures, hand gestures, facial gestures? Is it speech, etc.? The structure of the team, how many robots, how many humans? Adaptation, how does the robot adapt based upon that interaction, as well as the shape of the task. So the types of robot control, as we've already mentioned, include teleoperation, where the human controls the robot and performs localization and cognition, unstructured and not repetitive tasks. Semi-autonomous, where the human may control the robot sometimes, but there's a peer relationship. It only steps in to do perception or something when the robot is not able to do that. Supervisory control is where the human is involved, but routine or safe tasks are handled by the robot autonomously, such as the robot is following a wall, following a line, carrying something. The human may not be involved until maybe the robot has to transfer something to a conveyor belt and may need some feedback perception or something from the human. Shared control means the human provides tasks but interrupts the robot with perception or stops execution if necessary only. And once again, fully autonomous means the human initiates tasks but does not interact anymore with the robot after that point. So the Sheridan spectrum of control, once again, looks at from direct control, teleoperation, to robot acts autonomously, but this one is done in terms of teleoperation or remote control, mediated teleoperation, which means giving guidance periodically. One person might not be able to assume a number of roles for a particular robot, excluding the bystander role. And a number of people might be interacting with the robot in different roles and may be aware of different interactions happening as well as other information it may need. And assume it can determine information or interaction needs that may be different depending on who needs that information. And sometimes you may need a user interface to support a given role, like the teleoperation or modified teleoperation. And then we see the supervisory control to collaborative control to peer-to-peer collaboration. And then once again, dynamic autonomy, then robot acts completely autonomous. So here's another organization of the roles of interaction for a robot, where it could be mixed, where you could have the human acting as a supervisor, an operator, or a peer. Sometimes it may be such that the robot has the option of asking the human to assist where needed, or the human supplements automation in order to compensate for inadequacies. And this, once again, is the types of control where you have supervisory control, operators, teleoperation, peer is mixed initiative. Function, the human commands what happens. The operator, the human commands how it happens. Peer cross queuing based upon the needs, where they're in a collaborative peer relationship. So context required. Supervisor may be in a tactical situation. The operator may be needed for detailed perception, because remember, humans are better at perception than robots typically. Or peer may be a cobot, such as in a manufacturing facility where the robot and the human are working next to each other in a shared environment. So once again, the roles of interaction may be supervisor, operator, teammate, mechanic, programmer, bystander, where the human only steps in when necessary. Supervisor may oversee a number of robots and may or may not be able to have time to help any of them out, may have to hand off to another operator if something goes wrong. The supervisor needs to have a global picture of all robots in the mission and needs to understand when a robot is having a problem, the seriousness of the problem, the effect of the mission, and the challenge may be how many robots can a supervisor effectively operate. Or monitor. So for an operator, you may need to have a telepresence to understand where the robot is and what must be done. The interaction depends on the level of autonomy of the robot. It can vary from complete teleoperation to giving waypoints to giving high-level tasks to specify a mission. And there needs to be an awareness of the robot's health, environment, and awareness of what the robot is doing to support the task or mission, thinking about situational awareness. The challenges with this method is how to maintain awareness despite communication limitations, like there may be bandwidth limitations, especially if there's a long distance between the operator and the robot, and how many robots can be controlled by the operator. The next level is teammate, where the robot is seen as a member of the team. The teammate can give commands within the scope of the task mission. The interactions such as gestures and voice may be helpful for the teammate, and you need to understand any limitations the robot has and capabilities. The challenge for this method is the robot may understand the same interaction vocabulary as other team members, and if not, that could be a challenge. For the mechanic or programmer, this comes into play when the operator cannot resolve the issue. These interactions could happen within a task or a mission. Given that a hardware or software change is made, the mechanic or programmer may have a way of interacting with the robot to determine if the problem has been solved, like going into the internal workings of the code. Challenges with this method is how much self-diagnosis can a robot do to determine whether it's making, for example, adequate progress towards a goal, that it has lost a wheel or a gripper, and other things like the battery is dying and it needs to abandon the task to go charge, etc. And it has to determine when to move from operating in a degraded capability to pulling the robot off the task and attempting to fix the problem. The last approach is a bystander. A bystander has no formal training using the robot, but must coexist in the environment with the robot. It may consider a health or care situation, for example, a floor cleaning robot pets, or on the road driving. So in a military situation, a bystander robot could be a friendly or neutral or an enemy. And the robot must be able to protect itself from an enemy. Some of the challenges for this approach is how can a robot bystander form a mental model of what the robot's capabilities are when the bystander knows nothing about the robot? And should a bystander have a subset of interactions available? What type of social interactions come into play? An example you see of this a lot of times on social media is when the food delivery robots in a city either get stuck on a curb or get stuck against another delivery robot. A bystander, having no knowledge of the robots, may come along and help the robot off the curb or get two robots that are stuck together unstuck. So it's just about how much does a bystander, who may not know anything about the inner workings of the robot, have to or be, committed or want to actually help or interact. So robots for society. Robots for society are where people prefer to interact with robots like they do with other people. So thinking about the uncanny valley, when robots get creepy, they are more comfortable interacting with a robot that actually has some human interactive behaviors or characteristics. So robots should recognize and produce common human interactive behaviors. As social actors, they can fulfill new roles as companions, such as a museum guide, or as a peer or tutor for kids, or as a caretaker, and there should be some natural interaction, maybe in the language or in the facial expressions, and mediating behaviors and interaction between humans and increasingly complex socio-technical environments we inhabit. So in that method, you are treating the robot and the human as a system where each one has their role. They have a mental model of the interaction in the environment. There's some kind of behavior and response of the human. There's expectations of the human from the robot and of the robot from the human. Then they interact. They have some mode of communication, and the human is clear on the robot capabilities for the interaction. And when they come together, that creates HRI. So what is the difference between human-computer interaction and human-robot interaction? The main thing is embodiment. So obviously a robot is going to have a body. It's going to have, robots, but, as robots are in degraded conditions because you now have a robot. So you have some things that you may not have to deal with HCI, such as environment, odometry error, sensor error, mismatched motors, sensor failures, repeatability. If you have more than one robot, they may not respond the exact same way. Even if they have a model, they won't be exactly the same. Their sensors may not behave exactly the same. There are multiple roles of interaction. Multiple people can interact with a robot, and there are varying levels of autonomy. So different roles of interaction are possible. Multiple people can interact in those different roles. Robots act based upon a world model. And then once again, the degraded state may affect the operation of the robot. And there's a physical world of air, land, sea, etc. for a robot. And this intelligent system with a robot may have emerging behaviors, which means behaviors that a human observes that were not explicitly programmed. And the robot may also interact in harsh environments. HCI emerged as a field in the 80s with the dawn of computers and software development. So the good principles to use for a computer for various tasks include usability of interfaces, measuring of the quality of the interface, and oriented to the implementation, the effectiveness, efficiency, and satisfaction with which specified users achieve specified goals in particular environments. So learnability may be how easy is it for users to accomplish basic tasks the first time they encounter the design. Once users have learned the design, how quickly can they perform tasks? And memorability is when users return to the design after a period of not using. How is the usability, and should it be considered equally important, and what's preferable? If you have a high usability interface that does not help achieve the mission, then it's not very good. But if you have a low usability interface that manages to drive the user successfully to the goal, how do you evaluate that? And also, how do the users make errors on an interface, and how satisfied are they with the design, and how pleasant it is? In social robotics, interaction quality is very much dependent on the quality of the perception or sensing for the robot. In a lab environment, it tends to be simpler than in a real environment, where robots are seen as companions or teachers or healthcare assistants, and they express emotion. For example, the Pyro robot, which is a seal, was seen as a companion robot, where the robots encouraged Japanese children to learn English. The robot was placed in a basic school to interact with children. You can also see receptionist robots, where the robots have to understand a basic number of sentences and express emotions such as surprise, fear, anger, repulsion, or happiness, and sadness. And that the robot also must understand a basic number of sentences and be able to express emotion through facial expressions. Acceptable, reasonable behaviors are very much dependent on the cultural aspects where the robot is placed, because the people will set the expectations of how they expect a robot to interact with them. In general, the effect of a robot on individuals changes over time, meaning the adaptation or learning strategies required for the robot to continue to interact with the human. Models of human-human interaction suggest that there are different behaviors expected based upon proximity zones, each requiring a specific response or behavior by the robot. For example, human-human conversation distance should be within 1 to 2 meters. Human-to-human common social distance for a person who has just met is 1.2 and 3.5 meters. But human-robot distance could be within 0.5 meters. It is hypothesized that when robots look and act almost as humans, the emotional response by the humans when the robot interacts with decreases. not consensual among people doing robots. Not clear if the uncanny valley is uniquely to a human machine factor or can be generated by personal beliefs on what is the normal human appearance for a robot to have. In general, experiments do not decouple the influence of motion and emotional response, and hence the true value of anthropomorphism may not be obtained by HRI metrics. Information exchange. So the type of information that could be exchanged between the robots can be afforded by seeing, hearing, and touching when they're in close proximity, or when they are remote based upon a graphical user interface, or somewhere in between those two by gestures such as hand and facial movement. And this is done with speech and natural language communication, or telemanipulation, or telepresence. Or this example here, once again, teaching the robot by using a collaborative dialogue.
Press the red button. Turn all the buttons on. I can teach you to turn the buttons on. Press the green button. Now all the buttons are on. Can you turn the buttons on? Not quite. Press the red button. Now all the buttons are on. This is the blue button. Have you learned to turn all the buttons on? Very good.
And then robot teams. In search and rescue, multiple robots are managed by 2 or more people. UAVs are managed by at least 2 people. So there are several examples of this, such as swarming. And a fan out of teams may be a number of independent homogeneous robots that a single person can manage, or a number of independent heterogeneous robots that a single person can manage. Or as seen here, a team of robots playing soccer.
So adaptation, learning, and training, we just saw this with the Leonardo robot, where the goal of HRI is to produce systems that don't require significant training, such as using deep learning, machine learning, neural networks, etc. We're part of behavior design and task-specific learning, and then you identify interaction modes that invoke mental models so that the robot can continue to adapt.
Leo, this is Elmo. Can you find Elmo? Hey, Leo, look at Elmo. Wow, isn't he awesome? Yeah.
Leo's never seen this before. He doesn't know what it is. When Maddie introduces this novel thing, he gets really excited about it.
Hey, look at Elmo.
So Leo goes, oh, maybe I should get excited. He's picking up the emotional labeling, so to speak, of what Maddie's doing for these novel entities in the world, and then Leo's starting to adopt that.
Leo, this is Cookie Monster. Leo, Cookie Monster is very bad. He's very bad, Leo. He's a scary monster. He wants to eat all your cookies.
So the blue monster, Matt, isn't so keen on.
Exactly. It turns out that for children, when they're about a year old, a lot of what they learn is through this what's called social referencing.
He wants to steal your cookies.
Children learn things like if the mother actually like, don't do that, you know. They might not exactly do that. It's called social referencing.
He wants to steal your cookies.
Children learn things like if the mother actually like, don't do that, you know. They might not exactly know what it is they should be doing, but they pick up on that effect and they start associating like, that's a negative thing, I shouldn't do that. Or this is something that you like it, then I should probably like it.
Okay, Leo, I'll take him away.
He's designed that way actually to get people to want to interact with him in a way that's much more like a sort of parent to child or parent to puppy sort of relationship.
And we'll spend more time being more patient with
You might be more patient with it, you might enjoy it more, you know.
Now, I suspect what Leo is actually doing is simply linking high or low tone of voice with one of two colours, and then moving in one of two pre-programmed ways. But it doesn't matter, because I'm hooked emotionally.
Yeah, that's more like it. Come on, Matt, give him it. Have it. You can have it. Yay. Oh, no, he doesn't want it.
And so finally, there are many HRI applications and problem domains, such as using this to help the elderly or the people with different abilities. And we already talked about museum robots, receptionists, urban search and rescue. We saw robot soccer, also Robonaut, children with autism, such as by being a companion or a tutor. And much research has been done on this interaction, as well as on interfaces as a tool for robot developers, which is where human-computer interaction comes in, which has been studied for many years. But now the tools and metrics are being transferred over to human-robot interaction in the context of assistive and educational robots, entertainment, military, space exploration, reconnaissance, home use, manufacturing, mining, and agriculture, or in homes, such as for social robotics, companions, healthcare, helping the disabled, rehabilitation, exploration, or in hazardous or hostile environments. And this concludes Lecture 1. Welcome to class.